We can use Lewis structure to anticipate how a variety of different atoms might possibly share their electrons to achieve the octet rules and create molecules. The first example here has two hydrogen atoms, each with one valence electron, and one oxygen with 6 valence electrons. We know that each hydrogen atom would like to have 2 electrons, and the oxygen would like to have 8 electrons in their outer shells. What do? Well, each hydrogen atom shares its electron with 1 electron in the oxygen. This provides us with a single bond in between the oxygen and each of the 2 hydrogen atoms. So, we still have 4 electrons in the oxygen's outer shell. Those 4 electrons make up 2 lone pairs of electrons. We can draw this also as Kekule form, and the lone pairs are represented by 2 dots next to each other. This molecule is more popularly known as water. I'm sure you've heard of it. The next example involves 3 hydrogen atoms coming together with a nitrogen atom. Each hydrogen atom again has 1 valence electron, and the nitrogen has 5 valence electrons. We will use 3 of the nitrogen's valence electrons, each being shared with a hydrogen's valence electron, and this results in 3 single bonds being made, one in between each hydrogen and the nitrogen. And yet, there are 2 nitrogen valence electrons so far unaccounted for. These are left as they are and constitute a lone pair. We will also record this in a Kekule form. Notice we're still drawing the lone pair as 2 dots next to each other. And the molecule is called ammonia. Now we will consider something that's going to involve 4 hydrogen atoms, 1 carbon atom, and 1 oxygen atom. We know that the hydrogen atoms are going to want to gain an electron, whilst we also know that both the carbon and oxygen atoms wish to end up with 8 electrons. How does this happen? Well, 3 of the hydrogens will share their electron with one of the carbon's electrons. This creates 3 single bonds in between each hydrogen atom and the carbon. We're not finished. How's the oxygen involved? Well, the oxygen will share one of its electrons with the carbon and vice versa for a single bond in between a carbon and oxygen. The carbon now has 8 electrons. The oxygen has 5 electrons unaccounted for, and yet we still wish to add a further electron. We still have 1 hydrogen spare, so that hydrogen's electron will be shared with one of the oxygen's electrons to create a single bond in between the oxygen and the hydrogen. There are still 4 electrons in the oxygen's outer shell that we haven't had to share, and they remain 2 sets of lone pair electrons. We can draw this again in Kekule form, and this molecule is called methanol. It's very useful to transition from needing to draw molecules in Lewis form, as in the center, to being able to draw them in Kekule form, found on the right, as this is the common method used by chemists. Finally, let's look at a case where a double bond is formed. Here we start out with 2 hydrogen atoms, 1 carbon atom, and an oxygen atom. We know that the hydrogens are going to need to finish with 2 electrons, the carbon with 8 electrons, and the oxygen with 8 electrons. So, how is this going to happen? Well, we're going to use 2 of the carbon electrons to make single bonds with both of the hydrogen atoms. By doing this, each hydrogen atom has 2 electrons. The carbon atom has 6 electrons, so we still need to find 2 more. We have 2 electrons that are valence electrons that still haven't been shared, so let's share those with the oxygen. 2 electrons come from carbon, therefore 2 electrons have to come from oxygen, for a total of 4 shared electrons. And this must mean that we are dealing with a double bond. Now, the carbon atom has 8 electrons. Also, the oxygen atom has 8 electrons. Notice that 4 of those electrons weren't shared with anything and remain lone pairs. If we look at the Kekulé structure, the double bond is depicted by drawing 2 lines between the carbon and oxygen atoms, and the lone pairs are depicted by having 2 dots in close proximity to each other.